Please welcome everyone. Michal is a bioinformatician turned banker and turned cloud software company founder, and he loves Haskell and helping its community. Today he will talk about Agile generation of cloud API bindings with Haskell and functors, type classes, and higher kind of data types and how those may make your data analytics pipeline much easier to understand. So please welcome Michal, and whenever you're ready.
Hello. I will first report on our basically data pipeline project in Haskell, and then I will continue introducing the things that we use heavily in the pipeline. Just let me know what you are more interested in by asking any questions, and understand that this is the first time this talk is given in this format. So I may slip sometimes. This is joint work actually in Megabank because we deliver API bindings using this pipeline. So the problem we have quite often is that we have multiple cloud services. Everybody promises that they will take care of everything for you. So they are not just managed, but they are fully abstracted for you. But they need to be bound by ad hoc REST APIs. So you have really tons of documentation, and sometimes you have JavaScript SDK, which understandably doesn't care for most programming languages in existence, because only some of them have JavaScript FFIs. And definitely they don't take care about Haskell, but also they don't care about most of the languages that are highly specialized DSLs that are most useful in delivering software at a particular domain that you want to narrow yourself to. Then the next thing is that you want to make rapid changes to the infrastructure. So you use infrastructure as a code. So you basically want to write a code that will deploy the whole service on these REST APIs and make it work. And then you want to tear it down, right? So you turn down the whole service using automated script. If you don't do this, or if this teardown fails, then you may see the failure like Knight's Capital, which basically had the DevOps, very nice DevOps, but it didn't always work entirely correctly, and some of the errors were propagating through the deployments that were long ago to be basically finalized and removed. And this led to issuing orders for billions of dollars because the DevOps didn't properly tear down the old structure, and only because of that. So we have this tech stack inertia here, where we have fixed SDK language or languages, just JavaScript or JavaScript and Python, and nothing else. We have a fixed container sometimes, and we have also an option to use open API specifications for these APIs, but not actually most of the APIs do not deliver full specifications. So I mentioned that is a possibility sometimes, but most of them it is not. So we have this multi-cloud services, and then we recover the agility, right? So agility means that we want to use any language, any library, anything, reduce dependencies as much as we can. We want fast development process, and we want everything to happen reproducibly, right? And to combine best of different microservices from different vendors, like maybe Amazon DynamoDB combined with Google's hosting or Cloudflare workers, we would need to bind to all these SDKs for deploying of Cloudflare workers as the computation platform basically, and AWS DynamoDB. So that's also called multi-vendor cloud services, right? Also, only major vendors have the SDKs proper. So usually vendors just expose some APIs and tell you to your user REST. So you need to still write this SDK. There are also a lot of services that do not have SDKs because they are advertised as no code or low code. So they have webhooks, but most of the time you are expected to click through. And that's what we want to avoid because that's not really reproducible. So that doesn't allow you to write a program that deploys another program and makes sure that it's always the same. It's deployed always in the same way on every account, on every instance when you fix any bug. So the solution for us is to generate the code for API SDK bindings, just like people that use OpenAPI spec do. So OpenAPI spec basically is format where in JSON or in YAML you describe all the cloud API, all the REST endpoints, the data types on input and output, right? And then generate it in Haskell or in any language that you prefer. So for example, you can have a generation for Haskell and Elm and PureScript, and then you cater for long tail or specialized and very effective in practice programming languages that have some preferable domains. For example, if you are interested in integration, besides the fact that you want to do it on the cloud, you probably would use Mathematica, right? If you are interested in parsing, if you are interested in advanced algorithm design, you probably use Haskell, right? And maybe sometimes you don't use Haskell, you just use Elm because Elm has great Elm reactor, a very, very quick debugging for the front-end applications. So first we have Per API Scraper. I will not tell much about it because this is run-of-the-mill technology at the moment. It's basically using scraping in Python, which uses XPaths and then outputs the CSV file. Of course, since the source language here is untyped, is Python, then we need to really check the input that we get from the scraper. That's the general rule. So whether you do ethical scraping or you just deal with large data sets, you can always expect that most of the records may be correct, but some of them will not. We'll discuss it further. So we take it into Haskell, which gives you strongly typed representation. There is already some types safety in there, right? And then we analyze it to produce the code that is nice and easy to read, hopefully, and easy to use for the API binding. So we really have very little code generation because it's Haskell. It's very, very well-known techniques for code generation can be used. I can talk maybe about it another time in detail. I will just show the code that how it looks when it's generated here. And it's retargetable to other languages easily because there is a very little code. The general rule with Agile projects, your project can be very big. We cover many APIs, like over 5,000, over 6,000 API endpoints at the moment. But we do it within a small code base that is easy to analyze for us, which is in Haskell. So the issues that we have with the inputs. So first, there are multiple REST methods for all APIs. So there is get, put, and so on. There are call conventions, but they are not like C or Pascal call conventions because there you have like two call conventions. Basically, one is the call convention that you put the parameters on the stack before you call and then clean it after you call, and the other is that you clean it at the end of the call, right? And here we have a different call convention or parameter passing convention for each parameter, right? So for example, you may have a situation where you have one of these, and the parameter is passed as a path of you on URL. So basically here you have /VPC path, and then you have some string that indicates virtual private network ID, right? So that's one way of passing a parameter. The other is through URL query encoding, right? The other is as a special HTTP request header. There are really many ways of passing parameters, and they need to be all taken account to generate the correct code. You can, for example, use HTTP cookie and HTTP out header and request body. And inside this request body, there is a little bit of pain. It's actually JSON, so you probably want to have a representation that is a valid data type that represents this JSON, right? Because inside the user ID should not be string, here should be a number. Then after parameter passing conventions, the next pain is type conversion. This is the common pain for all API bindings, and there was a lot of work done for binding of the types of C calls, but for the binding of JSON, I'm only aware of the work of JSON autotype and QuickType, and there is of course JSON schema also, but the first two are attempting to be automatic, right? So the problem is that in Haskell we have very different realm of times from the representations in JSON, and you want to infer them. So we use the other program as a library, which is JSON autotype, to infer the best type representation. That is because usually the special data types like timestamp or user ID will be represented as strings or numbers, and you need to distinguish them, right? And usually in the documentation, you will only have examples. You will not really have the type declarations quite often, or not explicit ones. So this is the overview of entire pipeline. So there are 3 stages, basically gathering, which is done with the scraper library scraping in Python. Then there is parsing, validation, and analysis, which we do in Haskell. And finally, code generation, which we also do in Haskell. And the problem here is that if you try to implement the handling of 5 different libraries, right, this code will quickly multiply, right? And there will be more and more. So for example, there are 2 automatically generated bindings already on Hackage. One is for Amazonka for AWS, and the other is Google. And to my knowledge, they are done by the same author using the same methods, but there is a separate code for each one, right? This is the case we want to avoid, because we want to produce ideally a new API binding every week or every second week, right? So we have a common analysis for all the endpoints, for all the APIs, right? So we can support more of them. And that also means that we have a common handling of errors and common analysis that run on all the APIs to check that the input data is correct. Oh, and just in case you are interested about limitations, what we do not cover is custom HTTP transports. So, for example, AWS uses the custom transport for some calls, or custom encryption, or custom authentications, like in case of TransferWise, right? So TransferWise requires you that you generate OpenSSL key and then you sign your request in a special way. AWS also does it, but in case of TransferWise, you also encrypt your request. There is also, of course, the issue because most of this documentation is written by humans. We sometimes see the bugs in the documentation will propagate to our analysis or prevent us from using some endpoints. Also, some of the companies will only provide you JavaScript SDKs without really documenting the REST APIs. We do not cover techniques of how to connect to this and hope that it will become the thing of the past. At the moment, we are only aware of one such company. So the benefits are obvious. We have 1,000 API calls available within months. We can use basically APIs for many cloud services quickly. We can retarget it to the new language. And we no longer depend on vendor support, because that's a third point, because some vendors are very interested in supporting you and some have very small APIs and are only interested in supporting one or few particular users or particular market that may be not exactly you. Or they will ask you to pay for extra SDK development. Reducing code base also reduces the time to develop and maintain the project. I advertise it here as a paid service from Mega.com. So if you want your particular cloud API supported, then just please connect to us. Now the most interesting part. So I told you about how great things are, and now I show you how you can use Haskell to do a similar data pipeline at home. So that's basically the goal of this talk. Please use the techniques to prove that the Haskell is the best language available for data pipelines, for data analysis that needs to be robust and correct, right? First, we'll focus on aggregation because sooner or later we always aggregate data, and whenever we look for feedback, sometimes we look in the primary data at the list of records, for example, but most of the time we are interested in aggregation. That is the result of it. This aggregation may be a package, a whole package of all function bindings, and this may be also a summary of errors, right? Or summary how many endpoints are processable. So here, in this case, we have a basic unit of input, which is CSV record. So basically from Scraper, we get a CSV table, so we can conveniently view this table in any of your Office applications. So you may use LibreOffice, Calc, or similar for viewing it and check if it looks well and contains the right data, right? So we use very standard data formats here. And in each record in here, we will show much less than I've shown for the APIs. So I will not discuss all the parameters and all the paths and everything that you need to store for the endpoint. Just assume it's like a banking application. It's not much different. It just has more fields and correctness conditions are a bit more complicated. So in the banking application, you would have basically for each transaction a description, amount, and the date, right? Now we start to parse it. So we have a function that parses a list of strings. So we basically split the line or record in CSV into strings, right? And you will create a record. So that's a bad way to do it. So we have a type that obviously doesn't do what? Doesn't take care of any errors. So of course you can say, oh, in standard library we have maybe record functions for every case where we expect to have an error, and then we make case on maybe, right? So if it's nothing, then we do something. We make placeholder data, for example, or return empty output. And if it's just something, then we are happy and we continue our analysis. So that's also something that doesn't work. Assume you are handling 5,000 records. That's a really modest amount. And you do it always. So you do it in a monad, because maybe it's a monad. You propagate it, right? And what? If only one record fails, then your whole analysis breaks. So your whole aggregation yields no result if you return nothing. That's not very, very useful, because then you need to look at these 5,000 records and find the error where it comes from, right? That seems very, very obvious issues. So standard library also usually provide something like either why. So what happens, why it happened that you have no record, right? Or a record. And why is a string, so it's error message. Well, that's because the maybe is root of all opaque errors. So if you don't yield an error message, that is a problem. So then either y is also a monad, so you can continue and you will get the first error. And that kind of works better because you get one error, but if your analysis is complex and takes a while, that's not very time efficient, right? So this is the mistake that most Haskell libraries make, actually. They just return the first error message, right? And what you see here is if you have a single record failure rate of below 1 promille, right? So 1 in 10,000 records is failing. And you have a data processing pipeline that handles 10 records. Then you will rarely ever see a problem. Your chances of processing entire file without error is 99%. Then if you have 1,000 records, reasonable transaction database that you have on your bank account, right? Then you get 90% that first time on first try it will work, right? That's reasonable. You will fix this 1 or 2 errors and will go. But then if you scale this analysis, your chances are worse and worse. So if you have 10,000 records, you only have 30%, 36% chance that you will succeed on the first time. If you have 1 million of records to process, you really don't have a possibility that you will get it the first time. So you will run the analysis really many times, maybe 100 times, until we will get all the errors fixed in the input, right? That's clearly non-tenable. It doesn't scale to big data sets, right? So we do something else. First, we don't just provide an error message. We enrich this error message with the location, which is line number. So we have message, which is 1, and we will have also line number to find it quickly. So we quickly find where these messages, where this error came from. That will speed up fixing of the errors, because we expect, say, 100 times to fix the error. That will speed it up because we really jump to the right number, right line. And if our analysis takes a minute, then maybe in 200, 300 minutes, we'll have all the errors fixed, right? Well, that's not a very efficient use of your highly mathematical mind, because that's mostly waiting until the analysis is completed, right? Not really. For not so large data sets, that will still work. This is still something that you would like to avoid, right? So for even larger data sets, you always have a different solution. You return a list of issues, not necessarily errors. Anything that may be red flagged, that there will be an error later, or there is something you don't expect, like the transaction for amounts of 0, or an API endpoint that doesn't return any results, not even an error code, or maybe the API call that doesn't take any input, not even authentication. It's like, it's actually a static web page or what? So in this case, you probably want to make advanced warning, and because you just tell the warning, you just add the warning to your list of warnings. You don't stop processing anything. You can be generous about warnings, right? You start behaving like a compiler, because the compilers and static analyzers actually do this. So they take a huge amount of data and they aggregate it in such a way that you can quickly look at all the possible problems in the data that it will see. So you have a list of possible issues and a list of results. And with results, you continue your analysis. With the issues, you will probably report them. If you noticed what I told about the aggregation, of course you will aggregate them and start with these issues that are most frequent, right? Because that's the best feedback. But for now, we leave it because we have a problem here. Yeah, that's Haskell, and we lost our monad. At least, either was a monad, maybe was evil, but at least a monad, right? So probably we just lost something. Of course, not everything may need to be a monad, but we have a computation here, right? So if it gets sufficiently complex, you probably already learned that if it gets sufficiently complex, it's not just a plain function, but a monad, right? So there is something happening under the hood, right? So, maybe first we look at the issues. So list of issues is a monoid, so we can merge them like any list, right? Does it clue us what kind of monads we should have here? Yeah. We return two things: issues that will probably aggregate at the very end, and successes that will continue our computation on. So successes are probably a argument or the value inside the monad, and failures should be just hidden somewhere. So this is the plain monad writer, actually. You probably consider monad writer by the logging example, but the large-scale data analysis example is the best case where you see all the utility of monad writer. You can actually see even much more than on the logging case. Because, right, you now parse fields, you use a list of strings, and you have this monad writer that has a failures or a list of issues inside it. It's a monad, so it can be merged, and you can infinitely add more issues, and then you aggregate them at the end. And you have a list of successes. So your generic way of mapping your function over the data would be something like, if it's pure function, that it would be a little bit different, but normally this function will be a computation, will be a function in a monad. So you give the data to this function, then you either return a single result as a list so that it is monoid, or if you get nothing, then you catch it, tell into the monad writer, add to the log all your issues, and return this empty list, because then you have a monoidal result. That's nice. So your map data doesn't preserve the list length, because some of the elements of the list are foldable length. Some of the elements of the list will fall out, right? Because they will trigger issues that are not recoverable. But the analysis itself is quite recoverable. If it's very bad, you will get a very small list at the end, but maybe you have some successes. That would be an information, right? That we have 10% of successes or 5% of successes. It's much more information than you get if you just get the first error message and then it's 0, 1. You have a problem in line 100, right? So please don't manage large-scale analysis with error in line 100, not with either. It's not suitable. Use monad writer. And if you want to report more than just an error message and then more than a line number, and then you add the file name of the input, then you get more and more information about this issue, because issues are best debugged with more and more information relevant. Then you can learn a few tricks, right? Because you don't want to see the head of empty list error, right? If you made any program that uses head, what you see is that you write thousands of lines of code. If it's just 10 lines, it doesn't really matter. Thousands of lines of code, and somewhere deep inside there is head of empty list. Don't really know which list, which line number it happens. You don't know which data it is, right? So you add the information. As you add the information here, you just notice that it is profunctor, right? So you make an error map, you can add the things in, add more information to the data on issues, to all issues, or your error map, this is a normal F map on the monad, right? And then, for example, from JSON, you start prepend failure. You start enriching your information that is needed to debug the issue, right? So you, for example, prepend failure, because unfortunately from JSON is good. It allows you to have an error message, but only one error message, right? When it fails, it doesn't let you process entire JSON document, right? And tell, oh, there are 10 errors or 10 issues in 10 different places. But you can still enrich your error message. So you can say, we have a failure parsing this particular path or this particular attribute, instead of just minus A0 is not a number, because that's kind of puzzling, right? If you want even more, if you really like the profunctor story, I encourage you to look into contravariant logging articles. Unfortunately, I believe I don't have enough time to discuss them all in detail, but please ask me a question if you want. So then the next thing is you have this large analysis. So I give examples of few APIs that we process. Some of them are pretty small. They are just like 30 calls for Backblaze. Some are a little bit bigger, like Office, which is 1400 calls. For all of them, we generate the bindings. But you see, you also want to have a kind of overview about statistics of how many issues there are in the pipeline. So here we see that there are so many issues that we don't really hope to have them 100% processed. But still the result is useful, because you can write a program and deploy your application even if you have just, let's say, 80% coverage of the API. Most of the troublesome aspects of the API usually are hidden in some specialized fragment, like, I don't know, accounting API, or maybe a database query API that is out of band, so for debugging. So we always aggregate everything, and we always make it into a table. And then we list the statistics. And of course, since the statistics are not that informative, if you want to look at, for example, what is the error to fix first? Yeah, what will be the most impactful use of 10 minutes? right? So we should sort it by the error message, so by the type of the error that we have. So basically, we disassemble the error message, right? Then we sort by quantity, and then we tell it if it's an error or a warning, for example, from all. So now that we have it in non-monad writer, we can just extract a list of issues, sort them, classify them, and maybe even make a prefix tree on error message if you want to get advanced and have fully generic analysis. And then every minute that you spend on handling these errors will be impactful, because you will address the error that addresses not just one record, or just a minuscule fragment of your data, but a big data set, sub-data set, right? So the aggregation is actually very easy. The simplest case would be just breaking every error message by ends of line and columns, and just looking at the head and grouping by, sorting and grouping by, right? And then counting them. So this is very easy once you start using monad writer. Just need to write these 10 or 20 lines of code, and every time you will fix the bug, it will matter. Because you have a big analysis, you have 10,000 of records or 1 million or 10 million of records. You don't really want to care about errors that happen only for 100 records. Actually, if you look at the BCPS banking reporting guidelines, they also have like rule 2, your analysis should be always correct. Rule 5 or 6 is, but if it's incorrect, you check the impact, because if it's not impactful, you can ignore it. So now we are about to finish. So I didn't get to higher kind of data types. Maybe that's for the next time. But generally, they are helpful to differentiate how your data type evolves. So you gradually enrich it with information during your analysis. And I can shortly talk about principles. Basically, we use modified Agile core principles. So we aim for high throughput in fast iterations. We aim for best aggregation that gives you best observations from each run of the pipeline, even if most of the results are not there. So most of the data set ends in failure. And that allows us to skip over the schema issue or data quality in general issues. So maybe we have a lower data quality, but we can always rather measure the impact of data quality on the pipeline, not just make it an abstract rule. So I think that would be references for you. And if you have any questions, that would be the time to ask them before lunch.